Hello everyone. So today we will be starting with the new topic on differential amplifier, unit 3, differential amplifier. So in this, to start with about a differential amplifier, usually we have two types of signal in an electronic design. So one is single-ended design, single-ended signal, and the second one is differential signal. So in the single-ended signal means we measure the signal in terms of voltage or current with respect to any particular node. Like for example, in case of common source amplifier, we measure this output with respect to ground, right? So this is the N MOSFET where we give input for the gate terminal, and this is the load resistance RD, and this is the output at the drain terminal, and this we measure the output with respect to ground, right, or any fixed potential, right. Whereas in case of differential signal, we have two signal sources. See, this is one of the signal uh, subjected to load, and another signal. So we have two different signal. So these are the two nodes 1 and 2. We measure this with respect to each other, this being plus and this being minus, and this is the output what we measure with respect to each other. That is called as differential signal. So single-ended means we measure any one terminal or node potential with respect to ground. It is either node 1 with respect to ground or node 2 with respect to ground. So usually we define this differential signal as measurement between two nodes which has equal and opposite variations, right? We define the differential signal as measure of signal in terms of voltage or current between two nodes which has equal and opposite signal excursion. So this is the definition for differential signal, right? So now what are the advantages of using this differential signal or a differential amplifier? Advantage of differential signal. Say for example, in an integrated circuit we have different signals which are connected to different terminals or the different nodes. Say for example, this is one circuit which is giving an output at node 1, and this being connected to any particular other node, for example, right, and this is one of the input what we are giving like this, right. So similarly we have another circuit where we give an input signal in an opposite direction, and this is the measurement of output at node 2, and this is again in turn connected to uh, any other terminal in an integrated circuit, right. So in between this, say for example you have a clock signal, right, high frequency clock signal. So now what happens if there are two signals like this? If you have two signals, this is inverted with respect to node 1, means with respect to first circuit, this is inverted with respect to the second circuit. So here what happens, uh, when you have two signal and the signal with respect to the clock signal is very high frequency signal, say like this. So if you have two different signal, three different signals, two signals which are connected like this, and the very high frequency signal, if we have these types of signals inside an integrated circuits, what happens? This induces, since during the positive half cycle of this, so there will be a signal disturbance for the first signal in the positive direction, and again for the lower signal it will be having the same disturbance in the positive direction. Again when the signal is going down, so you have a small spike or a noise kind of observation you observe at the two different signals. So same thing we observe during the positive and negative cycle of this signal, message signal, or the signal which is coming from the node 1 and node 2, right? So now because of this clock signal, both the signals are affected, right? So both the signals are induced with a noise. There will be variation or disturbance in the signal, right? So this is what happens for the individual signal, single-ended signals, right? So now if you measure these two signal with respect to each other, right? With respect to each other means this being positive and this being negative, what happens? This being negative, plus and minus of plus is minus, and your signal what you measure between node 1 and 2. Okay, so now what I am drawing is the signal in between node 1 and 2, node 1 with respect to node 2. So what happens? So this is positive, minus of minus becomes still more positive, and this is the negative signal, and this positive signal and this positive signal get cancels and get a signal amplification in a single direction, where you get a complete signal, and in this signal there is no distortion, right? Basically the advantage, one of the important advantage is it differential signals are immune to noise. This is one of the important feature of the differential signal, where the differential signal are more immune to noise, and other is this differential signal are immune to power supply variations, right? So this is the another advantage of using power supply variations. If you have a power supply like this which are fluctuating, then what happens? If there the power supply fluctuation, then even in this case your signal will get fluctuated on both positive and the negative sides of your output of your individual signals, right? So this is what the advantage of using differential signal, right? So looking at this waveform, what are the requirements of having the differential signal? So one of it is high gain amplifier, high gain amplifier, right? And the second important requirement is circuit that responds to differential signal. So these are the two important requirements of using an differential signal, and the main advantage is these kinds of signals are more immune to the noise and any other fluctuation kind of thing, power fluctuation kinds of thing, right? So now these are the requirements. So for the circuits that we have discussed in the earlier, the available circuits which we have discussed earlier are common drain, common gate, and common source, right? So these are the three different amplifiers that we have discussed earlier, right? Using this, we need to come across how we construct or how we can use this differential signal across two different nodes or anything like that, right? So the main important requirement is high gain. Since we need a high gain here, so the common drain, we cannot use the common drain for the design because the gain of the common drain, the gain is very low. Gain is very low in case of common drain. And common gate we have a sufficient gain, but when we are using this common gate, the Zin is low in case of common gate. If we observe the common gate, where the input is given to the source terminal, so if we see the input from the source terminal, the input impedance is equal to 1 upon gm. This is very low, right? So that's why we cannot use this common gate for the amplifier purpose, differential signal amplification purpose, right? So whereas this common source, it has good input impedance and output impedance, which is suitable to design the required amplifier, right? So using this common source, we can try looking for defining the differential signal, right? So coming across, this is common source amplifier where we are giving input to the gate terminal and output is observed across drain terminal, right? So this is a common source amplifier. So this output or the output of the common source amplifier is usually given by minus gm into r times of V in. Okay, so the output is usually given in terms of gm into r times of V in, where gm into r is nothing but the gain of the common source amplifier. We have discussed about this during the small signal analysis and all. And here the input what we are giving is again a small signal over here, right? So this is the gain or the output voltage what we get in a common source amplifier, right? So this can be written as, so input V in with respect to the source terminal 0, right? So we can write the output expression as minus gm into r V in minus 0, considering two terminal of the circuit, so that we can modify this circuit to give the differential input now. Okay, to give the differential input. So now the same circuit we are giving one input to the gate terminal and the another input to the source terminal, right? So my output voltage can be written as minus gm into r into V in 1 minus V in 2, right? V in 1 minus V in 2. So this is the another way of representing the output signal with the two input, considering the differential signal, two different signal. Okay. So now whether this kind of amplifier is used to apply the differential signal is not we need to analyze here. Understood? So here we get the output which is equal to minus gm into r into V in 1 minus V in 2. Whether this kind of circuit can be used for differential signal. Okay. So now to analyze the same, we will consider one at a time, one input at a time. Okay, so now again we will consider the same circuit which is a common source amplifier. This is V in 1, okay, and the other input we are connecting it to ground. So this is for V in 1, okay, and considering for another circuit V in 2, so this is grounded, so this is R, so this is VDD, and this is for V in 2, right. So considering one input at a time, so here when we consider input 1, we are giving an input for the gate terminal, right. So we are giving input for the gate terminal, and the input impedance of the common source amplifier, when we are giving it with respect to gate terminal, the input impedance is very high. So if you remember the small signal analysis we draw for the MOSFET, it is open circuit at the input side, which implies that the input impedance is very high, right. So here considering the second input for the second circuit, second input which is given to the source terminal, and the another terminal which is a gate, another input terminal which is a gate is connected to ground. So this basically becomes a common gate circuit where we are giving input to the source terminal, right. But here in this case what happens, the input impedance seen with respect to source terminal, which is input 2, is very low, right. So this input impedance is very low. This cannot be used for an amplification purpose, because or this cannot be used for amplify properly. This will cause a loading effect when we are giving an input signal to the source terminal, right. So here to summarize, we have an with respect to input 1, input 1 will see a very high input impedance which is good for the amplifier, whereas input 2 will see very low input impedance which is bad for the amplifier. Now how to fix this impedance matching problem, right. How to fix this impedance matching problem, because so this is measurement of the signal with respect to two particular nodes with the signal excursion in an opposite direction. That is what we are measuring here, right. So I hope you understood that the common source amplifier for using a differential signal giving input 1 to the gate terminal and the input 2 to the source terminal will cause a impedance matching problem. Okay, so input 1 will see very high input impedance which is good for the amplifier. Input 2 with respect to source terminal will see 1 upon GM as input impedance which is very low, right. So now to fix this we use buffer. Okay, so we can use buffer. So one of the buffer circuits we have discussed is common drain amplifier, right. So one of the buffer circuit what we have discussed is common drain amplifier we can use. So we can modify this common source amplifier as, this is NMOS transistor, differential input with V in 1 given to the source terminal, and the V in 2 can be given through buffer. This is V in 2, buffer means which has an unity gain, and input to the source terminal for the common source V in 2 buff. Okay, and this can be common drain amplifier. What we are using is something a common drain amplifier. So here this is V in 2, right? So this V in 2 is given to the gate terminal, and this is NMOS device, and the output is taken at the source terminal, which is V into buffer, right? So we can use the buffer which has a very high input impedance and a very low output impedance buffer unity gain, right, which is a common drain amplifier, right. So now here what happens, we can give V in can be directly given to the gate of common source amplifier, but V in 2 cannot be given to the source terminal directly because of very low input impedance is seen with respect to source terminal. So what we do, we connect this input signal to the source terminal through buffer, right. So modifying this circuit, this is R, this is output of the differential amplifier, this is input 1 given to the drain terminal, input 1 given to the drain terminal, right, and this is the output of the common drain amplifier. You see, this is output of the common drain amplifier, which is a current source connected to this terminal, right. So this is VDD and this is VDD, and this is V in 2 given to the gate of common drain, and this is V into buff given to the input of common source amplifier, right. So using this you can observe that we can definitely give the input signal between the gate of two MOS devices, right. So one of the problem is solved, that is we can definitely give differential input signal between gates of two MOS devices. If you give the input to the gate terminal of the two MOS devices, with respect to gate terminal the impedance is very high. So this is M1 of common source, this is M2 of common drain, right. So this is giving the input signal. Now how to take the differential output, from the circuit, right. So in the previous we informed that, earlier we informed that the differential output is the measurement of two nodes with signal having equal in magnitude but opposite in direction, right. We defined that. So differential output is measurement at two nodes with equal magnitude, signal with equal magnitude but opposite in direction. This is one of the condition, and another requirement is both the node should have equal impedance. Only then it will have equal magnitude or the equal signal excursion, right. So now we will modify the same circuit here. We will modify the same circuit here. The first thing is common source amplifier, where V in 1 is given to the gate of common source amplifier, right, and another was common drain, where the input 2 is given to the gate of the common drain. Output is taken from the source terminal of the common drain and given as an input for the source terminal of the common source amplifier, and this is the current source at the tail. And as per the definition we mentioned earlier, right, so that it should have equal impedance. So what we do here, for this we will add an impedance R over here, so that it has an equal impedance. This is also R and this is also R, having an equal impedance, and this is both VDD which is connected, right. So this is the two differential input signal what we are giving, V in 1 and V in 2, and to measure the differential output, so this is VO1 which is given by minus GM into R into V in 1 minus V in 2. This is VO1, output of an common source amplifier with respect to, so this will be the V in 2, right. And similarly you have VO2 which is taken at this node. You see, this is VO2 which is given by minus GM, because both the transistor will have the same W by L. If it is, then GM is also same, minus GM into R, the resistance is also same, and V in 2 minus V in 1. This is the output of the second output with respect to V in 2, right. So for differential output we can write it as V out, which is VO1 minus, or VO1 minus VO2 as GM into R into V in 1 minus V in 2, 2 times of this. Understood? So this is the differential output, right. So this is nothing but a circuit of differential amplifier having an input which are differential and differential output as well, right. So this defines the differential amplifier with differential input, how we give V in 1 and V in 2, and having differential output V out, which is VO1 minus VO2, which is 2 times of GM into R into V in 1 minus V in 2. So this is differential amplifier circuit for you, right. Yeah, thank you. We will continue again in the next class.